let's go back to our screen to analyze what is happening with the central difference scheme. So remember, if we have a discontinuity over here, and let's take an extreme example. We have 1 over here and 1 minus 1 over here. Okay? So we have Burger's equation. So this is x, this is u. And u is 1 on the left and minus 1 on the right. In finite volume scheme, we are taking volume averages. So let's focus on the volume that encompasses the shock wave. And it turns out the volume average on this one is not 1, it's not minus 1. It's somewhere in between, right? For this one, because it has slightly larger region on the right-hand side, maybe the volume average is over here. And now problem arises. If we take the flux over here, it is not equal to the flux on the left-hand side, it is not equal to the flux on the right-hand side. Actually, the flux on the left-hand side and right-hand side are both equal to half of u squared, which is equal to half on both left and right. Oh, thank you so much. All right. Thank you. That's really useful. All right. Okay. Great. Okay. Yeah, it is not on the left hand. So the f of u should be equal to half over the entire domain, right? But if you look at over here, because u is halfway between 1 and minus 1, the flux over here is actually much less than a half. And if you average the flux on the left-hand side and the right-hand side, the interface flux at this point is going to be misrepresented, and actually by a lot. So the central flux scheme does not capture the correct behavior around shock waves. Okay, the correct behavior around shock waves, the interface flux on this point should only take the left value, and the interface flux over here should only take the right value, and that is the correct behavior. In order for me to capture the shock waves after it forms, we can't use central difference. We need to look at the direction where the solution is bumping into the shock wave. We should not look at the cell average that averages in between the shock wave. We should only look at the cell average that is coming into the shock wave, which means looking at the left cell average over here, looking at the right cell average over here. This is called upwinding. Why is it called upwinding? Because if you look at the Burger's equation with the initial condition like this, the solution here travels on the right-hand side, the solution here travels towards the left-hand side. It is like a wind blowing from the left on the left-hand side of the shock wave, and wind blowing from the right-hand side on the right-hand side of the shock wave. Upwinding is looking towards the direction the wind comes from, right, which is from the left on the left of the shock wave, and from the right on the right of the shock wave. And how can we tell if the wind is blowing towards the left or the right? The value of u. And how does the value of u tell us if the wind is blowing towards the left or the right? DFDU. It's DFDU, exactly. DFDU, or delta F delta U, tells us the speed of characteristics of shock waves. So that is what we should look at in determining if we should look towards the left or should look towards the right. If the FDU is greater than 0, we should look at the left. If the FDU is less than 0, we should look towards the right. So let's start modifying our finite difference scheme. Oh, I love keyboard. Okay. So I think we don't need that anymore. How do we close it? Plot layout. Command window. Let's close it. Okay. I now can maximize this. Okay, so if we want to change this from a central scheme to an upwinding scheme, we only need to change this line, right? So if we comment this out, this is the bad central difference, and instead FU interface is equal to, let's actually make it zeros, 1 and n plus 1. So okay, so in the beginning I'm going to say n is equal to length of u, and the dx, we don't need to evaluate this again, 1 over n, and fu interface is n plus 1, right? Because the interface includes the left and right points, and I don't need to touch the beginning or the end, I only need to touch the middle. So I'm going to loop for I goes from 2 to n. I'm going to set the interface flux, and here comes the if statement. Okay, and if the wind direction, I'm going to just say dfdu, right? Dfdu is what we are looking at towards the wind. If dfdu is greater or equal to 0, fu interface should be equal to of I should be equal to what? The left. Fu bar at I minus 1. That's right. That's right. Because at I equal to 2, I should be looking at the first cell flux. Else, fu interface I should be equal to fu bar of I. Yes. Oops. And so here now I populated fu interface in the middle by looking at dfdu. And what is dfdu? Remember, yes, dfdu is u, but dfdu, we are looking at the dfdu at the interface, right? And there are two possibilities. One is in the continuous region, we should be looking at the derivative of f with respect to u. In discontinuous region, we should be looking at the delta f over delta u. For Burger's equation, it's actually pretty simple, because the delta f over delta u is actually the average of dfdu on both sides. That's special to Burger's equation. We can't do that for general equation, but let's do it. dfdu bar is equal to just a u bar, right? So that's the dfdu in the cells, and dfdu interface is equal to u bar. Okay, let me actually do that. Let me actually just dfdu bar I minus 1 plus dfdu bar I. So because this is in continuous regions, this is an interpolation, this is the average between the dfdu on both sides. In discontinuous regions, this is actually delta f over delta u, right? Remember, the speed of the shock wave in Burger's equation is the average between the characteristic speed on the left and right hand side of the shock wave. So this takes care of everything. In general, it is dangerous to actually compute the delta f and divide by delta u, because if delta u happens to be 0 across these two cells, you are going to be dividing by 0, and you're going to get a nan, like not a number, and your solution is going to blow up. Okay, any questions about these several lines of constructing FU interface from FU that completes our upwinding? Any questions? If no, let's run it. Let's run it by first saying our initial condition, and we are gonna close the pictures, and I'm gonna copy this and evaluate. Okay, and let's see how it goes. Oh, undefined functional variable u bar. Oh, equal to u. Okay, I didn't. Yeah, so u bar is actually u, right? Absolutely right. So let me do this again. Burgers DDT must return a column vector. So let's debug this. It doesn't look like FU interface is a column vector. Oh, FU interface is not a column vector. I made it a row vector. Sorry for that. Okay, now this is a column vector. N plus 1 columns, 1 rows. Okay. Yeah, I don't code in MATLAB that often, so if you catch me doing anything wrong, please point it out. Okay, now we have the upwinding scheme. Now discontinuity forms. It stays a discontinuity and the shockwave dissipates itself. Right? So we see the solution keeps shrinking because the solution keeps rounding into the shockwave and dissipates out. All right. So upwinding scheme is one that is working for shockwaves. Any questions? Yes.
So physically, like the shockwave destroys information, right? So if you try to have information across the shockwave talking, like such a scheme would never work.
If I have, yes, shockwave destroys information. That's right, because the characteristics runs into the shockwave. If you have things, if you have a solution on two sides of the shockwave talking to each other, it doesn't necessarily doesn't work. But like if you have a small amount of information transferring, that should be fine. But like you shouldn't rely on like different sides of the shockwave talking to each other.
So if you use like a really high order center difference scheme or something like that could actually work.
If you use a really high order center difference scheme, I don't think it'll work. Yeah, the reason is that a shockwave not only loses information, it's a naturally dissipative phenomena, right? And it's something that increases entropy. A central difference scheme, on the other side, you can there are some very good research doing analysis on central difference scheme. Interesting property is that it conserves some metric of entropy. So you wouldn't create the right behavior of the shockwave, like increasing entropy, by having a scheme that conserves entropy. So the upwinding behavior is it's something that creates the right behavior for a shockwave. It dissipates information in some sense.